Thank you so much. It's an enormous pleasure to speak here at this conference. Peter is very important to me. So important I showed up on time for my talk. And everyone's been saying so many nice things about Peter. I figured it was up to me to balance the scales a bit. No one's actually asked me to do this, but it's the last day, and I figure it's too late to find a new speaker. So Peter taught me a lot mathematically, but he also taught me a lot of other things, how to handle pressure and stress. There's little that's more stressful than being Peter's first-year student and meeting with him for one of the first times. During my generals, I remember at some point Peter asked me to classify real division algebras. And I beamed, and I opened my mouth to answer the question. And he stopped me immediately. He said, no, he's too happy. Let's move on to a different question. I also remember, I'll never forget this, I remember I was at Peter's office at like 8 p.m. And Ali Altug and I had been working together on a project at your suggestion, and we proved some result about equidistribution of zeros of L functions of curves. And I was excited, so I went to tell Peter. And again, Peter got up, and no, very emphatically, you didn't prove this. You couldn't have proven this. Let me explain to you why. 5 minutes in, I was completely convinced, and I left his office thinking to go over the proof and see what's going wrong, what we were confused about. 10 seconds in the elevator, I realized Peter was full of nonsense. The proof was completely correct. And that's a very important lesson I learned, that even brilliant, confident, loud mathematicians can be wrong. And Peter was wrong a fair share of the time. There was the result by Booker about L functions. There was the proof of QUE for holomorphic guys by Sound and Holowinski that Peter had a role in. Recently, there was a local to global principle for Apollonian circle packings. And to be wrong so many times, you have to make a lot of significant statements. So I wish I was wrong half as often as you, Peter. Peter is always the happiest to be wrong. He always loudly and proudly goes around telling everyone about his mistakes that move in a significant direction. And Peter, I hope you keep confidently yelling, and I keep being allowed in the room to listen to your remarks. All right, that concludes my stand-up routine. Thank you very much. Thank you. So let's move on to mathematics. Everything I talk about is joined with Samuel Grushevsky, Gabriele Mondello, and Riccardo Salvati Manni. And the result I want to talk about will specialize in a second, but the basic setup is the following. Take X to be a quasi-projective variety, and we'll move to C very quickly, but for now you can stay over any field. And the question you can ask, sort of informally, is how far is X from being projective? So there's kind of two ways to approach this question. The first one I'm going to say is top-down. So what you can do is you can look at the minimum dimension of the boundary in a projective compactification of X. You can measure this, and sort of the smaller this is, the closer X is to being projective. Or you can go bottom up So I'm going to define m dim some c, maximal dimension of a compact of X, to be the maximal dimension of Y, where Y is in X, and Y itself is projective. And this sometimes is I mean, none of these notions are perfect. This notion is sometimes useful, but sometimes it's can be a little misleading because you could have some special large compact dimensional subvarieties of X, and everything else that's compact is much lower. So it can be more natural to consider a slightly revised version, which I'm going to call m dim sub c gen of X, which is the same thing. But now I'm going to want Y to contain some point little x, where little x is a very general point of capital X. So I want a variety, a compact variety of this dimension through an arbitrary point of X, or at least through a very general point of X. So there's some obvious inequalities here. Namely, if I look at MDCX, it's at least as big as m dim c gen X, which is at least as big as the codimension of the boundary -1 for any compactification of X. This implication here is obvious. If you have a large variety through any point, you obviously have a variety that's large. And for the other direction here, you use Bertini's theorem, which is why I sort of said projective instead of proper. If it was proper, it'd be a slightly different game, but with projective, once you have a boundary, you can just start cutting by random hyperplanes, and you eventually get rid of the boundary. Okay, so we have these kind of inequalities. And for a lot of varieties, it's extremely difficult to compute any of these notions. We're going to focus on these two specifically. I don't really want to say it, so I probably won't. But over C, I just mean, you know, outside the union, let's say outside the countable union of subvarieties, for example. Yes, that's right. Thank you. Same thing.
Is another way to say it, we take the minimum or little x of the maximum dimension?
If your field is big enough, yes, but that can be a little frustrating, actually. I'll give another way to think about it over characteristic p points in a bit. But yeah, it's not such a hard notion to define. I just don't want to go into the specifics of it right now. Other questions? Okay, so I immediately want to focus in on the main structure for the talk, which is AG, the moduli space of, I'll say, PPAV, principally polarized abelian varieties. I only pick principally polarized because it's a concrete thing to pick. If you change the polarization, none of these notions change by sort of obvious reasons. They're too close to each other. They have finite maps to each other. And just to normalize our discussion, the dimension of AG is GG plus 1 over 2. So, okay, what is known about these quantities? Well, if you work in characteristic P, so I'll say over FP bar, there's a pretty large compact subvariety of AG. So you can get at least as big as GG minus 1 over 2 by considering the locus. I guess I have some colored chalk. Let me see if I can use this. By considering the locus of abelian varieties, whose p torsion set, just as a point, is just the identity. So if you have no p torsion, this will give you a compact subvariety of this dimension. As far as I know, this is not known to be the largest subvariety of AG. I believe that's still an open question. Well, okay. If you work over characteristic 0, there is a result of Kiel and Sadoun from about 20 years ago. Basically saying you can't replicate this over characteristic 0. So they get a bound of g minus 1 over 2 minus 1. And it's no coincidence, this will show up in our discussion later, that this is the dimension of AG minus 1, or specifically the symmetric space of dimension G minus 1. That's kind of the key case they have to rule out from happening. And finally, if you use the Bailey-Borel compactification, that gives you a compactification with small boundary. It depends how you look at it. The boundary is dimension G minus 1 over 2, which is still quite big. On the other hand, it's codimension G, so it's much better than you sort of naively get. And this implies, by the inequality we wrote down there, that over C, the maximal generic dimension of a compact subvariety is at least as big as G minus 1, again, just for using Bertini. Okay, so that's kind of what was known. And so, the theorem I want to talk about, which is entirely over C. I'll say a little bit about what we can do over other fields. So there's two parts of it. First of all, we compute this quantity exactly. So if you go through a generic point of AG, and we can even say what it takes to be generic very explicitly, then this is exactly equal to G minus 1. So you don't have G-dimensional compact subvarieties through arbitrary points. And secondly, if you just look at the absolute maximal dimension of a compact subvariety of AG, we get this exactly. Let me extend these equal signs so I have room here. Okay, there we go. So it's G minus 1 up to 16, which is really cool. And then I'm very proud of myself. I used to have two cases, one for odd and one for even, and I realized how to combine them. So it's G over 2 floor squared divided by 4, floor down again. Yeah. This is serious stuff here, people. Okay. For G at least 17. And so it sort of starts out being what you would expect, no surprises, and then eventually you get quadratic growth. And just to emulate my colleague Grushevsky, a little table here just to viscerally see what these numbers are. So here's G. And let me just write the dimension of AG, the Kiel-Sadoun bound, the generic dimension, and just the absolute maximal dimension of compact subvarieties. So this is GG plus 1 choose 2, so it's like 6, 10, 136, 153, 50, 50. The Kiel-Sadoun bound gives you these numbers, so it's a big drop-off, but it's a linear drop-off. This is a very easy one to write. It's just G minus 1. So it drops significantly. And then at 16, you get your first little bump. Though actually here they meet up again, and then this guy becomes larger. And all the way at 100, you get 625, this guy over 16. Oh, come on, really? Where? Where does it match? If G is less than 16, I'm sorry. This is G is at least 16. Thanks. Now is it okay? Now it's okay, yeah. Mm-hmm. Thanks. Okay. So these are the numbers. So a remark. So first of all, the high-dimensional compact subvarieties, while they're rare, they aren't generic. You can deform them in particular. They're still dense, even topologically. As I'll explain, will become obvious from the construction. But in fact, it's obvious even without the construction. The point is, and I'll say a little something about this, is we have Hecke operators on AG, and so as soon as you have one large dimensional compact subvariety, you can apply Hecke operators to get others, and Hecke operators give you dense orbits. So once you have one, you know that you have many. And the other remark that I'll give, well, not remark, I guess, but everything I want to talk about is we were sort of really happy with this result, but the main question that one would like to answer is what's going on for MG. This is a much harder question. Basically, no matter what you're doing, just because AG has got a symmetric space structure to it, so it's much easier to approach. MG is a lot trickier. So we don't learn much for MG from this, but we learn a little something as a formal consequence. So just to set the table. Yes, so MG, that's where I'll start, is the moduli of curves. So smooth projective curves of genus G. And we're actually going to look also at MG compact type. So these are curves of compact type. Which is basically, you take a bunch of smooth curves and you glue them together at points in a tree structure, and that gives you curves of compact type. You got to be careful about P1s. But this naturally sits inside this, because if you have one smooth curve of genus G, it does it for you. G at least 2, let's say. And then you have this diagram, which is where the application comes from. Let me draw it, then I'll say something about it. This is the Torelli maps. So here's AG. If you look at the Torelli map from MG, it actually doesn't just land in AG. It lands in AG indecomposable, which is AG minus everything which splits as AI cross AG minus I, as I goes from 1 to G minus 1. So everything which splits not just as the underlying abelian variety, but also with a principal polarization, of course. And MG lands here. And there's different advantages to both of these maps. So this one in particular is injective, if you're careful about stack structures and stuff. This map here is proper. So in some ways better. On the other hand, if you look at this map, you have positive dimensional fibers. So it's very far from being injective. The reason simply being you can take the points along which you've glued these curves and move them around. And that gives you these large fibers, which are products of the underlying curves, basically, over different components. of AG. So if you're trying to use results here to bound dimensions on either of these guys, you have some problems. Here you're sort of not being a proper map can hurt you. And here you have to sort of lose the dimension of the fibers because you aren't seeing what's going on there anyways. I don't really want to say right now, sorry. Largely because I'm not so comfortable with it myself. This is like the not me part of the paper. But afterwards I can tell you if you come, we can work it out. Yeah, but you have to be careful. Yes, I mean, you know that's true, right? So I'm guessing yes? Yes, okay. Confirmation. Confirmation. Okay. One more time, I'm sorry? And you direct sum them as principal abelian varieties. That's right. Mm-hmm. Okay. So what's known about MG? Well, there's a result by Diaz, which tells you that this is at most G minus 2. If you look at the maximal dimension of a compact type thing inside MG. And there's a result by Zhao, building on the works of other people, that if you want a lower bound, you can get log base 2 of G minus 1. I believe this requires G at least 3. So the way to do this is not through any of the methods we're going to be talking about. This is through some sort of inductive branched cover sort of argument and being careful. But these two are very far apart, and this kind of discrepancy is typical with doing stuff on MG. And I certainly have no idea which one is correct. People I've spoken to seem to believe this is the closer bound to being true, but it seems to be a very difficult question.
Is there a nice way to think about these things? I mean, what does it tell me about the moduli space?
Absolutely. So both this and the one for AG, any moduli space, tells you that if you want a compact base with an abelian variety over it, a family of abelian varieties, or a family of smooth curves of genus G, where the fibers sort of vary, so you can always cheat by base changing somewhere very big, then the bounds are exactly this. Okay, and Kiyossadun, also largely motivated by this, prove that if you look at MG compact type, you get an upper bound of 2G minus 4. There's sort of a balancing game with MG compact type, because if you go to the more degenerate strata, you get larger and larger sort of free dimensions just by collecting the fibers over the J map. On the other hand, they become smaller and smaller, so you don't know sort of which stratum will win out for you. So let me say what we get. As a result, we get some improvements. It's hard to recall them all precisely, but two notable ones are if you look at the maximal dimension in MG compact type of a compact subvariety, well, we get it exactly. It's 3G over 2 minus 2, but in a limited range. So for 2 between G and 23. And basically, the way to do this is you can construct this family explicitly, and then before the quadratic bound gets too scary, you can just sort of import it. And it's good enough. Eventually, it's quadratic, so it gets too scary, and then you have to know something about how the compact large dimensional subvarieties of AG intersect sort of the image of MG, and that's a hard question which we can't really answer. So we have this, and on the other hand, we also have that if you look at the maximal dimension of the image under the Torelli map, of MG compact type, which is just the usual Torelli map sort of closed. This is bounded above by G minus 1, again, up to 15, before the quadratic bound takes over. Some modest improvements, but still some new results you can deduce from MG for dimensions that aren't too large. And there's one really cool thing that comes up. If you work this out, what we get is if you look at AG indecomposable, so you remove all products, non-trivial products of PPAVs, then we can show this is bounded above by G minus 1 simply because it sort of lies inside AG. On the other hand, the boundary of AG decomposable now is just one dimension larger than the boundary of AG inside the Bailey-Borel because you've removed A1 cross AG minus 1. Elliptic curves cross abelian varieties. You compute it, it's one worse. And so the trivial bound, lower bound, you get is G minus 2. And we sort of thought for a while this is correct and tried to prove it through conjectures that were false. And now I don't know. I don't personally have a guess as to which one is correct. But it's very tantalizing because of this two possible options. Yeah.
Is that a lower bound for all G? No, above it.
This one?
Yeah, is that a lower bound for all G?
Yes, yes, yes. It's a lower bound for all G. Yeah, this one's not hard. I mean, you just take a product of a bunch of low genus curves explicitly, you take some families, you get this bound. Other questions? Okay, so before I say something about how the proof goes, let me say something about FP bar 2, where we can't prove anything, but I can use it to sell propaganda, because we have sort of a conditional result, and it's conditional on something I've been curious about for a while. So at least now I can sort of motivate others to think about it. So if we work over FP bar, I was asked before by he how I define MDMC or MDMC gen in particular. And the way to define MDMC gen over FP bar for AG, or indeed any field, is you can say that, well, what you really want, if you want something to have to a very general point, is you want a compact subvariety which deforms. So the way to set it up is you want some relative family X over S and a map from X to AG over FP bar, such that this map here is dominant. This map here is proper. And the dimension of pi is exactly this thing. So this thing being at least k means you can do some setup like this, because this is telling you for every point of S, you're getting some k-dimensional fiber, you look at its image, and it's moving around, and it's covering all of AG. The reason this is better, well, the reason this is how we do it is because over FP bar, there sort of are no very general points. Every point is either non-ordinary, or if it's ordinary, it's CM, and then the CM type kind of tells you a lot of combinatorial information. Essentially, FP bar is countable. But more than it's countable, every point really is special in sort of its own unique way. So this is a way to get around that. And so expectation this is my expectation. I haven't run this by my co-authors. So if it's wrong, you know, it's not on them. But I have no idea what MDMC is. But if you want MDMC gen over FP bar of AG, this is equal to G minus 1. And what's true is if you assume a formal transcendence result, sort of an X-Chanuel type theorem, which I'll explain if I have time, then I can actually prove this. Our proof goes through, just for this case, for MDMC gen, if you have this kind of statement. So there's a lot of sort of very easy to think of function transcendence as solved, especially because the methods keep getting better and better. But then you want to try to do something new, and nothing works. So in characteristic P, a lot of these transcendence arguments just sort of fail. They rely a lot on tools from logic or differential algebra that become very, very tricky in characteristic P. So these kind of statements are still very much open. This is over FP bar. It's probably a good time to pause for questions again. This is sort of the summary of the results. Okay, so let me say something about the idea of the proof. Idea of proof. And the basic idea is very simple. Basic idea is to take the boundary and deform it out into the interior. Because where does our heuristic come from? It comes from the boundary in the Bailey-Borel compactification. Now, if the boundary were ample, in the appropriate sense, if it moved around everywhere, then the heuristic would just work. That would give you the correct answer for the maximal dimension of a compact subvariety. It doesn't, it's not ample. You can deform it in general, but we still, because we're in this specific setting of AG, the boundary does deform in a very specific way, which we can then attempt to use. So let's assume, to begin with, that X is an AG. It's proper or compact, and its dimension is at least G. So we saw dimension G minus 1 is nothing special. We can expect anything there. But if it's dimension G, we can expect to learn something. And what we're going to do is I'm not actually going to talk about the Bailey-Borel boundary explicitly. It's not necessary. But you can sort of see its shadow here. We have this map iota of the parameterizing the decomposable locus, or a piece of it, A1 cross AG minus 1 to AG, just by taking an elliptic curve and a G minus 1 dimensional variety and direct summing them. This map is not injective, but it's good enough. It's finite, so essentially it's injective. Everything here is, of course, completely insensitive to taking level covers, or finite covers in general. And what's true, we go to a new board just so I have some room. Maybe I'll leave these numbers up, is that if you take that map and you think of it as a family of AG minus 1s inside AG, then as the elliptic curve guy goes to infinity, goes up to the cusp, this exactly degenerates the Bailey-Borel boundary in that compactification. So a way to say that is that as your elliptic curve goes to infinity, the image of this fiber inside AG also goes to infinity. Okay, so what does that mean? Well, your X is compact, so it's not going to intersect it for big enough E, but of course, everything inside this story is algebraic. So that means that for almost all E's, all but finitely many, I don't know if the prime is visible, I'll make it a very big prime. For almost all E's, you learn that X intersect this fiber is empty. So this kind of thing is not going to be too useful for us, because what if you don't have intersections? Then you're sort of out of luck. What we care about is having intersections. Then we can look at them and try to show that they're special in some way. So in fact, what follows is that for all E, because you're allowed to intersect still at finitely many fibers, if you look at X intersect this fiber, it could have intersection, but the intersection can't be the correct dimension. Because if it's the correct dimension somewhere, then if you deform a little bit, your intersection can't vanish. It has to be preserved. If you intersect in a degenerate way of larger than dimension than you expect, then it could sort of go off. If you imagine like two planes inside A3, they could be identical and they could move off, but if a plane and a line meet at a point, you can't wiggle them and get rid of that point. So this intersection is nowhere likely. Or likely in the notion, in the sense of the dimension is what you would expect. Okay, so this is looking more in line with sort of the functional transcendence story. This is already something unusual about X. But of course, the problem with this kind of approach is that, well, that's great, but what if X just doesn't intersect A1 cross AG minus 1? Then you're out of luck. But luckily, this isn't the only game in town. There's many other ways to deform the boundary out into the interior. And an easy way to think about it is through Hecke operators. Which I'll present in sort of, to me at least, the simplest incarnation. So we're going to let HG be the Ziegel upper half plane. So the set of symmetric G by G complex matrices whose imaginary part is positive definite. So if G equals 1, you just get the usual upper half plane. If G is bigger, get something more complicated, but it behaves very similarly. Then the part of the story we'll need is just like SL2X on the upper half plane. There's an action by symplectic matrices on HG. And if you quotient out by the integral points, this is some discrete action, up to sort of stacky points, which don't matter for us, you get AG over the complex numbers. And importantly, if you look at H inside SP2GQ, you could use the projectivized symplectic group, but these are enough for us. And you look at the multiplication by H map, so take Z and act by H, you get some graph on HG to itself, some holomorphic isomorphism, which will descend, if you're rational, to a finite correspondence, which I'm going to call T sub H. This is my Hecke operator. Inside AG cross itself. So now I can use it in the usual way. Given the variety, I can act by this TH and get another one. And so what I learned, using the exact same reasoning, but now applying Hecke operators to all of these guys, I get a different deformation out. And I learned that for all elliptic curves and these elements H, if I look at X intersect a Hecke translet of one of these AG minus 1s, this is also nowhere likely. Okay, so now I'm in what kind of story? Well, I have this compact variety. I have this dense set of countable dense set of subvarieties inside AG that sort of go everywhere. And they sort of go everywhere in the jet space as well in an appropriate sense. And X, if it intersects any of them, the intersection is unlikely in this sense. So this is already much better than before. But you still run into the same problem. You know, what's to say that X can just not intersect all of these guys? And in fact, that happens. The actual guys that realize the bounds we prove will not intersect these guys. So we got to address this problem. Okay, so to do that, what you do is you think of all of these translets as leaves of a multifoliation. I'm not actually going to define or use multifoliation, but morally speaking, that's what's going on, that even though these guys are sort of countable, they're sort of the integral parts of a multifoliation on AG. So concretely, how do you think about this? Well, we got this map pi from Ziegel space to AG. What we can do is define X tilde to be the inverse image of X. So now this is not always, but most likely, just some transcendental analytic subvariety of AG. It's not algebraic. Note that AG is not an algebraic variety, but it's open inside G by G symmetric matrices, so it's as good as algebraic. You can basically talk about an algebraic structure on AG, either using semi-algebraic sets or by completing in C. That's sort of not a problem. So the situation you're in, you sort of have this map of analytic varieties, which is local isomorphism. You have two different algebraic structures here. X tilde will stop being algebraic. But what you can prove is now for any H is in SP2GR, if you look at X tilde and you intersect with the sort of analog of this, but without descending down to HG, so there's the action of H on a iota of just a point Z in the upper half plane cross the uniformization of AG minus 1, HG minus 1, the natural analog of this, then this is also nowhere likely. Because if this were somewhere likely, you could wiggle H a little bit, get H to be a rational point, and then it would descend to one of these guys, and that's a problem. So you sort of go from this one deformation inside AG to this countable family of deformations to now, using this by now standard trick that Pila sort of introduced, Pila Wuzani, angel the subject, to this sort of real family, which you can only really see on HG. But if you wanted to, you could define the whole thing as a multifoliation on AG. There's nothing truly transcendental that's required here. Okay, and the advantage of doing this is finally these points exist, because the symplectic group acts trivially. So by picking my H appropriately, I can actually force intersections to happen. And now I learned something. Intersections are weird, they're nowhere likely. Okay, so that's sort of how transcendence theory enters the picture. And of course, at the end of the day, skip ahead a tiny bit, the exceptional guys are going to be some sort of Shimura variety things. And this is sort of telling you that one way Shimura varieties are special is that if you want to take the Bailey-Borel boundary and deform it out, you can sort of only do it through Shimura varieties in some appropriate sense, which is kind of interesting. All right. So where does this all go? Well, now we're sort of firmly in this functional transcendence world where we have an algebraic variety in AG. We're intersecting it now with these guys, which are very simple algebraic varieties in HG in appropriate sense. And these dimensions are always too big. In fact, even if they were too big once, we'd learn something, but they're always too big. So functional transcendence tells you this only happens in very particular ways. So I'll just give the highlights. So there's the theorem, first of all, by Ulmo and Yafaev, which the main ingredient in the proof is a monodromy theorem by Andre, based on work on the Lean, that says that if you have a subvariety V in AG, say an irreducible subvariety, and its inverse image, say a connected component of its inverse image, is algebraic, which you can think of as take the Zariski closure inside G by G matrices, and that'll have the same dimension as its inverse image. So it's algebraic in both worlds. Then that implies that V is what's called weakly special. So it's almost a Shimura variety, or really, if you take a product of Shimura varieties inside AG, it can be a fiber for one Shimura variety over the other. These are easily seen to be algebraic. The content is, to have this property, I mean, to be what's called bialgebraic. The content is that these are the only guys that do it. And then there's another theorem, which in this context is due to Mock, Pila, and myself, though by now it's known in a whole bunch of different contexts due to a whole bunch of people, starting with Ax. So I'm going to call this sort of Ax Samuel for AG. It's true for Shimura varieties, variations of Hodge structure. There's a bunch of different contexts where it's true and a bunch where we don't know that it's true. Which basically tells you that, so this is only talking about guys that are algebraic in both worlds, HG and AG. But in a very precise sense, if you have any algebraic information that's passed along between the two worlds, it must go through one of these weakly specials. They're the sort of the gatekeepers to passing things back and forth. So the concrete statement is very convenient for our purposes. If you have an algebraic guy upstairs and downstairs, this is technically weak X Samuel, what I'm saying, but it's the one that's always used by everybody. If you have algebraic guys, and you have U inside their intersection, so to intersect them, I got to take the guy in AG and pull it back to HG. So this is some analytic component. And it's unlikely in the sense that the dimension of U is larger than you would naively expect. So it's at least as big as dim W plus dim V minus the dimension of AG. Then what must be responsible is the existence of one of these weakly specials. So there exists a proper weakly special in AG. Such that the projection of U down to AG sits inside S. So really, you can easily make these kind of examples because you have these S's that are algebraic in both worlds, and then you can sort of fake an intersection that's too big by first deciding on the intersection inside S, and then picking something in HG which contains it, and picking something in AG that contains it, and you've made a big intersection. And this is telling you that's the only way to do it. So this, in some sense, looks like sort of, the first time you see it, maybe, if it's your first time seeing it, it looks a little, maybe not random, but not all that canonical. But it turns out in sort of a formal model theoretic sense, this is really telling you that statement about algebraic information that you can quantify and make precise. Okay, so I don't want to talk about this too much, because I talk about it too much as it is. But the point is we're in exactly this setup now, that we have our X downstairs that's compact and algebraic, and we have all those guys, those translets, up in HG. Their intersection is too big, so there must be these weakly special guys showing up. I'm sorry, I don't actually remember. Do I have until 10, or should I stop at 9:50? How has the world been working? It's been 9:50? Ah, okay. Okay. It's good to have clarity. I'll just be 5 minutes, and I'll finish at 9:55, making no one happy. Okay, so just to jump to the chase, to cut to the chase, there's a little bit of cleanup work to do, but we get the following conclusions. So conclusion 1, if X contains a Hodge generic point, it's a point with no special Hodge classes in any of its tensor powers, and X is compact, X and AG. Then the dimension of X is at most G minus 1. Basically, this can't happen. Look at that translate through a Hodge generic point. Some weakly special thing must be involved, but Hodge generic points aren't contained in any weakly special guys. So automatically, you get this dimension bound. And the next corollary we get is actually a classification of the maximal compact subvarieties of AG, and not just a dimension bound. That if X is maximal compact, then X looks like S cross x prime, where S is in some AG1, x prime is in some AG2, where G1 plus G2 is equal to G. S is a compact Shimura variety, and x prime has dimension G2 minus 1. So up to isogeny, this is all of them. This is the best you can do. Again, there's some work in doing this, but it's not too bad. And so then, once you have this theorem, the key to answering the question, you just answer what is the largest dimensional compact Shimura variety inside AG. An easier question to ask than answer, because classifying Shimura subvarieties, it's kind of like classifying semi-simple Lie groups. It's a little easier in some ways, a little harder in others. Luckily, people have kind of done this over Q, which I found incredible. You can, with a few exceptions, kind of write down, at least to isogeny, every single semi-simple Lie group over Q pretty explicitly in terms of quadratic forms or Hermitian forms or symplectic forms, some version of that. And so you go through, you do a big case check, and let me write down the maximal example. So how do you actually get this G squared over 16, more or less? So what you do is you take a CM extension of a real quadratic field, E over F. You pick a Hermitian form on e to the 2g of signatures GG for one embedding of F and 2g comma 0 for the other embedding. You want it to be definite at one real place in order to make it a compact Shimura variety. This gives you a symplectic form on q to the 8g, because E is degree 4 over Q. And this gives you an embedding of the resulting unitary Shimura variety into A4G. The dimension here is G squared. And so this gives you 1/2 of your maximal examples. You also have another one for guys of the form 4G plus 2. So these are the maximal guys. And this is essentially all of them. At least the Hermitian symmetric space structures has to be exactly this one. You can mess around a bit potentially with the Q structure. We haven't sort of classified that, but that's one example of what you can do. Okay, so to finish, I just want to say what this transcendence result was over finite fields, or FP bar, which will allow you to get the generic statement. And what it is the following. I'll say it very quickly. So if you take a point x in AG in the ordinary locus of FP bar, and you complete AG at little x formally, this is a formal group, then this is a formal torus by Serre-Tate theory, because deformations of abelian varieties are the same as deforming their p-divisible groups. So you can show this is a natural structure of a formal torus. And what you can do is you can pick a formal subtorus T just as a formal scheme. You can take a variety V inside AG, passing through X. And now you can assume that if you take V and you complete it at X, you get some other formal scheme at this point X. You can intersect it with T and assume that this dimension is unlikely, is what you would expect. Then this comes from the reduction of a Shimura subvariety. So I'm cheating a bit in that this is, I'm not actually cheating, but this is stronger already than a conjecture of Chai called the Tate linearity conjecture, which tells you if you have a formally linear subvariety, then that comes from a Shimura subvariety, but you can strengthen it to something like this. And if you had this kind of statement, it's very much an X-Chanuel type statement because you have different kind of algebraic structures on the completion, which I'm thinking of as uniformization, and the same proof would generalize to give you this result I mentioned. Okay, thank you so much for your attention. Correct. Correct.
So I don't remember asking you that question at all, for example. Maybe I foresaw that you would need to classify these at the end.
It's all useful. It's all useful.
Yeah. But anyway, I think your comments have convinced me to keep quiet.
Next question. This is supposedly, this last statement is a transcendence result.
It's a transcendence conjecture. It's not a result. But yeah, I would think of it that way. Yeah, this is a conjecture. Sorry. Yeah, this is very much a conjecture.
Actually, I have a question. You mentioned these much more general transcendence results that are now known using more model theory. What do they include? What setting besides A?
Oh, by now, what can we sort of do?
Yeah.
So at this point, there's two the main generalization of the method is this result by these four authors, I forget all their name, Blasquez, Freytag, who use differential algebra. They've actually removed model theory from it entirely, thinking of leaves of sort of foliations given by first order equations, and just looking at the monodromy there. And so that very much generalizes this setting. It's sort of any first order differential equation. They can do something if you have certain conditions met. That includes the setting of mixed Hodge structures. And I have a paper with Ben Baker where we show that sort of includes the case of all periods and families. It's almost equivalent, actually, close to equivalent, morally equivalent to the setting of just take any family over it, look at the transcendence of the full periods, not just the Hodge structures. So we have that setting. It does not include things we want, like most notably the Simpsons correspondence of the Betty stack and local systems to flat bundles. There's a transcendence sort of game there waiting to be played. The only result, I think, is due to, well, Simpson had some results on trialgebraicity, and Abhishek Oswald, my student who was a postdoc here, he had a result in the rank 1 case. But in general, that setting is open, and there's some other settings where we don't know how to do it. But anything with a differential equation, we know how to do now.
If you have one, then you can use vector operators to produce a lot.
Yes.
Can you say, like, if there are many different...
Oh, yeah, for sure. I mean, just from the example, right? Because if the Heck operators won't change any of this structure. So there's definitely countably infinitely many families. You can then ask, are they all of this type or something? And you can probably even answer that question, but we haven't worked that out, yeah.